this. Hello. Hello, hello. Boom. Hello. How are you doing? I hope you are doing well. Hello, this Friday. Yep, no worries, no worries, no worries. Yeah, just listening. We're waking on a paper. What we're doing. Let's see. Can I zoom in? Can I zoom in more? Can I I don't know if I can zoom in here. Well, can I just do like that? Will that work? Will that work? That'll sort of work. There we go. Okay, cool. Cool. All right. So we have a little bit of complexity on our screen here today. Because we are working on okay. 1 second. There was supposed to be a more dramatic change when I hit the button, but then it didn't load properly. So, but no, don't do that. Do this. Do this. There we go. Okay. We are working on this papier. Right. So, all right. So just to read through what we got going on. I guess we have a little bit of time before we need to get started, but basic plan, basic target is we are going to see if we can nail down some of these things we're discussing with the ionospheric RCS, the application of the radar equation or radar range equation, whatever you want to call it, to our ionosphere bounce shenanigans. And we started a little of this before we have done, and so I will read through kind of the math pieces and alignments where we have gone and where I think we need to go. Oh, you know what I need to get? Hold on. Give me 1 second. Okay, good. Ba 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 da 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 da. All right, let's see. So this is the update. That wasn't what I wanted. Did this have the thing in there? Yeah. Okay. Did this have it? This has some, right? So, question of time. Okay. Okay. Not that. That's not though. No. That is not what I wanted. It's not that document then. Update docs. Calc. What's this? No. That is not what we wanted. Oh, geez. No. No. Okay. Where can I find that? I might be able to find it in. No, close this. I might be able to find it over here. I'm sorry. I'm just I'm looking for a document that I made a little while ago. That I know I sent to someone on my committee, and so I'm trying to locate it. Let's see. It would be sent. Okay, let's see what we got. What's this? Well, it's all they send. No, that's the same thing that I was looking at in the other place. What are you? Huh. I know I had them somewhere, and I cannot, for the life of me, find where. Oh, wait, hold on. Is it in here, maybe? No, not that. Oh my goodness, where is it? No. I am going to flip out. You know what? I do not know where this is. I do not know where this is at all. Okay, well, we're just gonna eat it. That's what we're gonna do. Oops, did not want to do that. Okay, so we can drop this. So I apologize for the extended. As I tried to find the document I was looking for that I couldn't find, but I'll kind of explain where that's. That's going to be going in a moment. Right. So, here is where we're sort of starting, right? So we're going to look at we're going to start with the monostack. This is the generic radar range equation, right? We're going to start here. So power at the receiver is power transmitter times gain of the transmitter, gain of the receiver, your wavelength squared over 4 pi cubed. R is your distance from your transmitter to whatever you're bouncing your signal off of, right? So it's R squared out and R squared back, and LS are your total losses. And then if we convert that into sort of a volumetric piece, right? So theoretically, each of these is happening for every element within a volume. Then that becomes an integral over the volume, right? The power, the transmit power is the same. All these things are constant. Actually, the loss isn't necessarily constant. We'll see that down there. Right. So, and then we have our transmitter receiver gain, right? That's all constant. Or that's all a function of theta and phi. So kind of your look angle at your transmitter and your look angle for your receiver. Or I'm sorry, it's the same look angle here. I'm sorry, because this is still monostatic, right? And then over R to the fourth, again, it's the same. R is for each point in your volume that you're looking at. The sigma, right? And so sigma is the instantaneous. So this is the radar cross section instead of just being a single radar cross section because you're bouncing off a single thing. Each point now theoretically has a different radar cross section that's based on your location in the volume, right? Where in the volume you're looking at can theoretically have a different radar cross section. So in other words, bounces a different amount of the radar energy back to the radar. Okay. So now we are going to take this into a bistatic version while keeping the volumetric adaptation. Now, again, transmitters out here. There's our wavelength. There's our losses. All we've done is we've said, okay, we're going to look at everything from the receiver's point of view. So there is some mapping from receiver's point of view to transmitter point of view, which, by the way, I think I might invert. Yeah, I'm going to invert all of this. So everything's going to be from the transmitter point of view, not from the receiver point of view. So I need to do that. Just to... All right. Nope. Where are we? Here we go. So let's see. Are we here? Yes. So this, we need to change the G sub T to... Okay. Yeah. So we want G sub T as a function of theta. Hold on. Did I already switch this? That means we're mapping... Hold on. G sub T... Yeah, right. So we want to go kind of invert these two, right? So we're gonna go we're gonna go theta R. Oh no, did I just copy again? Damn it. All right. So it's gonna be theta R as a function of this jazz, right? Only these now need to be T, right? T, and phi sub R as a function of T, right? And then these are going to be G, where is it? Now we need G sub T should just be theta T, like this, BT. Let's see, G, T, theta T, phi T, and then J theta R as function. Okay, yeah, right. And now it's V T. Okay. Right. So what we're doing is we're looking at everything from a transmitter point of view. So now I'll explain why. Give me a second. So we're going to nope. Bring this up. Okay. Let's Let's zoom in. Oopsies. Zoom in a little. So let me explain to you why. Let me just get some area here to write on. Okay. So let me explain to you why we're doing what we're doing. So what we want, right, is we want in the end losses as a function of say R and theta. Now, what we're looking at now is the top-down view. This is in the end what we want, right? We've removed the third dimension. We're looking at top-down view. Here's our transmitter. And then you're going to go out some distance where you have the skip distance, right? And then you're going to have some losses out here. So what that means is if you're going to build this mapping, you need to be looking from the transmitter point of view, right? Not from the receiver point of view. So what we need to do is we need to translate all of, so now looking at 3D again, looking up in altitude again, right? So compressing a different angle, right? I'm going doop, doop, right? So here's my receiver. I have some, if I look along this line, right, it's some RR theta R phi R, right, to get to that point, and some RT theta T phi T to look at the same point, right? Because these are just going to be different angles, right? That's just a different theta than this is. Right, and there are different ranges and blah, 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 right? But what I want to do is I want to say, okay, all right, yeah, so, kind of. So what we're looking at is signal reflections, so a radio frequency signal reflections off of the ionosphere. Right. So we're starting at some transmitter. We're sending our signal up. We're reflecting it back down to some receiver. Right. That's kind of what we're doing. Yeah. So, right. We're scattering within the atmosphere. Now what we're trying to do theoretically is, break this down to the point where I can have some two-dimensional loss field, right? So if I'm looking down, right, I would have my transmitter. I'm going to have some skip zone over here. And then I'm going to have some loss. I can say, okay, if I go out to here, I should be able to identify approximately what my loss should be here, given a certain ionospheric state, right? So yeah, I mean, these are all coming down to Maxwell's equations, but it's kind of a messy subdivision of it, right? Because what's happening is I'm propagating this RF up into the ionosphere. It's interacting with free electrons, that are in a plasma, cold plasma in the lower ionosphere. Eventually I'll kind of super refract off of it. I'll essentially reflect off of it, because as I go up in the ionosphere, my electron density is going to increase. I'm going to end up reflecting off a point there. Yes, if you do it that way, yeah. Yes. Long story short, yes. I'm trying to avoid the Green's function route if I can. So the problem is what I'm trying to do, right, is I'm trying to say what my absorptive loss is up here, right? Yeah. I mean, this is all really classical electrodynamics. It's just messier because you have all the plasma shenanigans that's going on. And so what we're going to do is, ideally, we're going to set it up to where we have this, like I said, we have this sort of loss field identified. And we could say, all right, under these sort of standard conditions, and you can have, there's sort of a list of geospatial environmental conditions. So what your the intensity of your UV flux is, if you have any high energy particles going on, if you have geostorming going on, what the density of your neutral oxygen, O2, nitrous oxide, N2, all this stuff, right? So all these things are kind of going to go into it. But ideally, what I can say is, hey, I expect to see a loss of X at this point for a single bounce, right? So if I'm looking at a single bounce reflection like this, I should anticipate at this location approximately a loss of X. Then I go out and I measure it and I say, oh, my loss wasn't X, and my loss was actually more than that. And now I can start, you can start doing a kind of a N plus delta N for your index of refraction. You could start trying to back out some of the loss terms that are coming there, right, from that error term. But so theoretically, the idea is to be able to have a simple or a relatively simple method of guesstimating, I guess, but sort of giving an initial estimate of what I would expect my loss to look like if I'm bouncing my signal from my transmitter here to a certain point out there at a certain frequency. Oh no, you are 100% correct because I didn't hit the transition. Holy cow. Awesome. Well, thank you. I've only been doing this for like a year. You can't be expected to know things. I apologize. Yes. Let me show you a little better what we're talking about here. I'm so sorry. Thank you for giving me the heads up. I have too many things on screen at the same time. If I have more than one thing going on in my head, my brain just runs off the edge of a cliff. So anyway, so let me go back through that a little, right? I have transmitter, I have receiver. I'm doing this sort of bounce thing off here, right? I've got my my theoretical transmitter here. There's a skip distance where long story short, the signals are hitting the ionosphere from within this skip distance are going to pass straight through, and they're going to go out to space. Oh, very cool. Very nice. Yeah, this is some weird amalgam of engineering and physics. So you'll see why in a second. I might end up doing so. Typically, how you might like simulate this is you'll have some representative ionosphere, and you'll do a what's called a ray trace through it, and essentially you're doing kind of like your optimization of a path, and so you find the most likely path. I have not found solitons yet. I've not encountered solitons yet. So anyway, the whole goal is to avoid the ray tracing shenanigans, right? But there's a couple different ways. So if we go look, and I'm gonna intentionally translate back to this, right? That I literally did nothing. Okay. There we go. So if we look at the other side of this, sort of where we're starting from, I don't know if you saw this beginning, right? We're starting from the radar range equation. And so what this is looking at is received power for a given transmit power, a gain on your antenna gain, right? And system gain is kind of shoved in there as well. Your frequency, your 4 pi cubed because of propagation losses, your distance out and back, right? So you have an r squared out and an r squared back. Your various losses are shoved into a single L, and then your radar cross section of whatever you're looking at, which is sigma, right? We can go from there to a volumetric version of it, where because we're not just bouncing off a single point, we're actually propagating through a part of the ionosphere. Each of the point where we're propagating through is going to have some what's it called, Bragg scattering associated with it, right? So some of that Bragg scatter is going to go off in different directions. If you're looking like this is initially set up for a classical radar system where your transmitter and your receiver are co-located. So you're looking kind of at the Bragg scatter back along, right? The back scatter. That's what's going to come back to the transmitter. And now you have a differential cross section, right? So each part of the volume that you're looking at is going to scatter different amounts back to your radar that you're going to receive as your receive power, right? And so, yeah, so we hop from there to this sort of volumetric version of it. And from that volumetric version of it, now we have to go to our geometry that we were looking at, where our transmitter and receiver are in two different locations. So that means we've got a transmit gain and a receive gain, right? These are theoretically going to be different at different angles from the transmitter and receiver. And then we have now our transmitter distance and our receiver distance. Ah, shoot, I need to switch those around too. Anyway, so, and then again, we're integrating over our volume that you're looking at. So now what we're looking at, so now if you think about it, I did not even change that again. I'm good at this. Okay, so if we look at what we're looking at now, I've got my transmitter over here, right? And I'm sending up my my waveform, like a plane wave that's encountering some volume. Wow. Awesome. I know what 3 dimensions look like. It's fine. Everything's fine. Right, make that parallel. We got, oh my goodness. Anyway, we make that parallel. Pretend that looks parallel, like an actual cube or cubic prism. Right. So at each point in here, you're gonna have this messy, really clouds of electrons that are kind of different ways. And so at each point, you're going to end up with some Bragg scattering that's going in this way and this way and this way. And so some of that Bragg scatter is going to get towards your receiver, right? This would be the backscatter piece. This would be the receiver piece, right? And you're kind of integrating over all of this shenanigans that's going on in here. By the way, this is not isometric either, because you have magnetic field lines, right? Earth's magnetic field lines are going here, so you're going to end up with what's it called? Cyclotronic motion of the electrons around the field lines. Yeah, so I need to look at how this is all going to fall out, because I'm not really sure yet. Kind of, yes. If you think about it, we're looking at from here to here is a single point, right? So you can kind of hemisphere it a little bit, right? Theoretically, you're reflecting off of a part of this towards. Yeah. Oh, 100%. Except the problem is it's too big to do like a classic FEM or FTTD kind of task, right? Because you're talking thousands of kilometers theoretically. So you have this Bragg scatter piece, but you also have a specular piece, and this is where most of your. So the question is, can you ignore the Bragg scatter? I'm not 100% sure. I'm probably going to keep it in here for kind of completeness at least. And I am basing that piece off of a paper that was trying to define the radar cross section for the ionosphere itself. And so that's where a lot of this like volumetric shenanigans comes from. So I'm gonna have the Bragg scatter piece in there based off of that paper. But most of your energy is gonna come along theoretically come along a ray path, right? Yeah, so there's a bunch of ways you can simplify this, right? Because it gets even more complicated because your transmitter is not actually transmitting in all directions isotropically. So you're going to actually have, an antenna pattern that looks kind of like this. So you'll have more power here than you will have here. And the same thing's going to happen at your receiver, right? So your receiver is going to have some pattern where it's going to have higher gain here than it will have here. So you also have all of these elements of like the engineering piece that are kind of playing in here. Typically what's done, right, is again, they go back to a ray tracing. So you're kind of assuming that most of your energy is coming from a specular reflection, right? And if you go by that assumption, it's still complicated, but it's a little bit easier because you really have a single ray that you can kind of think of it propagating along, right? And it's going to start going through these layers of the ionosphere until my plasma frequency is equal to my signal frequency. And then I'll get this reflection piece, right? And so what's going to happen is I can say, oh, well, my loss is just the sort of absorption loss from this path. So if you go by that, this is where I'm actually kind of interested in something because I don't know if this is a way to do it. What this reminds me of, yes, I believe so. So what this reminds me of a little bit, if I have the definition of that correct in my head, then I believe so. This reminds me of the path, what's the name? Feynman path integration, right? Where everything sort of collapses down to a classical path. In under the assumed classical conditions, right? So there might be a way to just apply it that way. Because I think this is essentially doing the same kind of thing. Because it's really just it's just like old school ray optics, pre what's his name? Not Fresnel. Why am I forgetting? Fourier, pre-Fourier wave optics, right? Like Newtonian wave optics, which is kind of how they end up assuming things translate down. So the goal of all of this is to sort of say, well, I should have some expected loss here, and then if I have some delta, I can then use that to start questioning what's going on in up here, right? So when I go back to what I was doing, let's see, shut that back off again, right? To what we're going back here, right? What we're going to do is we're going to say, all right, we're going to pretend these are isotropic, ideal isotropic radiators for our transmitter receiver. So the gain goes to 1. Yeah, you might end up having to do the full Fourier optics shenanigans. I hope I don't, but it's possible. But yeah, let me just kind of explain where I'm at so far and kind of where I need to go, or where I'm thinking of going with it, right? So we're going to assume, I'm going to assume our transmit power is 1. I'm going to assume our gain on our transmitter and receiver are 1, because again, I'm trying to back away from the engineering piece into a sort of baseline physical assumption, right? So what I get is something closer to this, and now this eta right here, right, is the positionally dependent radar cross section, right? So it's the radar cross section at each individual point. So here's where I'm thinking, and then what I did is I split the loss. I brought the loss terms inside the integral because you should get some loss, right? You're going to get absorptive loss from within your volume. You're going to have absorption loss, and you're going to have what's called deviative loss. So for deviative loss, what's happening is, as you're getting close, as you're approaching your plasma frequency, which is an indication of how much, how intense your plasma is, how many electrons you have squeezed in there. As your signal frequency approaches that, you actually end up getting this slowing of the wavefront in it, and then that wavefront ends up diverting into different directions. And some of that will go out into space, and that's called deviative losses. And as you get, again, as you approach, it gets more and more important as your signal frequency approaches your plasma frequency, that deviative loss becomes substantial. Before that, it really doesn't. But the hope is to essentially break these down with the index of refraction equation that we're going to come to in a minute. And eventually get down to a relatively simple, I'm hoping a bunch of things will cancel out essentially, and we'll end up with a relatively simple loss definition for our kind of ideal loss as a function of range and angle from your transmitter. And then you can kind of plop that down, and then that becomes your kind of baseline from which you look at deviations for things, right? That's the idea. I don't know how effective this idea is going to actually be in the long run, but it's the thought process. So I'm going to go back into my OneNote here, and please, if this doesn't make sense in some way physically with things that let me know. I am far from I'm trying to figure this out as I go. I'm currently a PhD student trying to crank through some of this stuff. So yeah, if you see something, if you have an idea, please do tell me, because I'm always looking for those. I are dumb. Hello? Okay. All right. Right, so we have a few different things that we're playing this off of. Now, if you've never messed with plasmas before, I'm going to show you some fun shenanigans. Where's the modern version of it? It's over here. It's in this one. Boop, 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 boop. No? What? Is it not in here? Oh, that's not. Oh, no, this is Zowdy. Is it not in this Zowdy? It might be in another one. Where's the Appleton-Hartree equation? Trying to find the modern version of Appleton-Hartree here. There we go. There we go. The index of refraction term gets a little bit messy when you start dealing with plasmas. So, yeah, no, that's fair. Yeah, Lagrangians get, depending on where you end up with Lagrangians, they get freaking nuts. Yeah, so essentially our index of refraction, this is sort of the guiding element of what's doing all of our losses are buried in here. We've got our our X term is the plasma frequency over the signal frequency. I think it's angular frequency, so same thing. Where plasma frequency is electron number density times E squared over M epsilon naught, M sub E, so it's the electron mass. And so this is really telling you the pure interactions of your, is this visible? Yes. Okay. The pure interactions of the, just the free electrons with the RF signal coming in, right? Y is your magnetic field line term, and your magnetic field term is going to cause you some issues. Long story short, because of the cyclotronic motion, the angle between your signal impacting the magnetic field lines and the kind of the direction of those magnetic field lines matters. And what's going to happen is you're going to end up with a split direction of propagation here. And one of these is called, because these were defined in the 20s, so they came up with names like this. One of these is called the ordinary mode, and one's called the extraordinary mode. And there's a plus minus that comes in here. But yeah, so Y is the gyro frequency divided by your signal frequency, right? And the Z term is your collision term, which is dictating all of your absorption pieces here, right? So it's just nu over omega, where nu is the collision frequency and omega, again, is your signal frequency. No. So the Earth's magnetic fields are going to be much stronger, right, than than the magnetic fields that are part of your signal. And so, but what's happening is you kind of have right. So the electric fields in your signal, what they're trying to do is they're trying to oscillate those electrons, right? But those electrons have their own motion, and so if you're coming in, if you think of it this way, if you're coming in along the direction of the motion of those cyclotronic electrons versus if you come against the motion of that, determines kind of how much you're able to wiggle those electrons around to for them to re-radiate out the signal that impacted them. So that's really what's happening. Yeah, it's just kind of the momentum and movement and cyclotronic, or the gyroscopic movement of the electron is going to just split off into, you get extra momentum in certain directions, essentially. So you end up with a splitting of your signal. Yeah, and then so this collision frequency actually is a lot of different collision frequencies sort of piled together. You have electron collision frequency. They actually will use a circular Earth when they do the ray tracing and stuff. The initial setups, yes. The initial ray tracing setups, they did use flat. And when it comes to like this intersection here, that's essentially flat. Right? You don't have to necessarily deal with these, but the angular distortion or the angular change of the magnetic field lines in the longitudinal direction. But if you're looking at the transmit to receive distance, you actually do need to look at because these are the positive use case of these is over the horizon communication, right? So this is how you get like an AM radio signal beyond line of sight, essentially, right? And you can pick it up at night, but not during the day because you have extra losses during the day from the lower parts of the ionosphere. Right. So in the end, all of that shenanigans comes together to give you that index of refraction. That's determining your propagating signal direction after, as it's going through there, as well as things like the losses and the splits. So if you notice here, right, this plus minus is where you get the splitting of the ordinary and extraordinary modes that are all functions of y, right? This is where your y term comes in. So if y is 0, you just have a simpler plasma. Y is 0, all this stuff goes away, and so you just end up with x over 1 minus iz, and that's your right. Yeah. So they're similar. It's essentially a quartz crystal, right? You have no magnetic field going through it. It's acting like a just kind of a more standard propagating thing. Right. So what I'm really interested in is what's going on with the loss, because the losses on the bottom side ionosphere, so that's the D and E regions are called. It's where you end up with a lot of loss, especially at lower frequencies, like I'd say 5 megahertz and below. And a lot of these losses are electron neutral interactions. The axis is the magnetic field direction. Which axis? Yeah. Uh, oh, um, not necessarily. Um, Let me think about that. The axis of symmetry is the magnetic field line direction. Um, Off the top of my head, I could see why that seems reasonable. Um, except you're looking. So the problem is that your signal propagation direction is not symmetric around that axis, though. Right? You're coming in on a vector in a single kind of line vector. Whoa, shoot! From the ground. So this field line is going along the sort of along the longitudinal direction of the Earth, and then your field line is coming in. Okay. Crystal axis along with both rays. Yeah. I don't know as much about the propagation along the crystal. That does make sense, right? That does make perfect sense because it's which direction you're going to have the repeated structure in, and you're going to have a kind of line of symmetry along a specific. Yeah, I that would make sense. I think things are a little more amorphous with the ionospheric stuff. In that you don't have these. It is gonna split is the problem. So it is gonna split, and you're gonna have to track both paths along which the signal splits, because you'll end up with multipathing between your transmitter receiver, right? And it's again, it's going to be the ordinary and extraordinary mode, and each of those is going to have different amounts of absorption. So you are going to have a ray split. That being said, there is a way to tell what the ratio of kind of like, think of it like a reflection transmission rate coefficient. There's a way to tell how much of your energy is going to be in one versus the other. So and I did this a little while ago, and I can't remember off the top of my head, but it's called ordinary because usually, in most cases, you end up with the ordinary mode under certain, like, if you're in the exact right angle, if your transmitter to receiver is along the exact right angle compared to your magnetic field lines, your extraordinary mode will matter more. But we're gonna kind of track both of them. And so if I go, hold on. So for example, in here, where he's talking about the absorption piece, right, this is the ordinary piece here, in this, and here's the extraordinary losses, right? So I was kind of like going through some of these papers and diverting, just pulling stuff out of these papers. So I haven't finished going through this paper all the way, but you'll see he splits into the two different modes that propagate, two different propagation modes that kind of occur. But yeah. In addition to all this shenanigans, just to make things fun, there's also a whole chemistry chain that's occurring, that's giving rise to your electron densities and to the neutrals and the ions that are floating around, all of which have different cross sections in their collisions with the electrons. Oh, and by the way, some of those produce secondary electrons as part of the chemical reactions that happen. So sometimes you'll end up with sources of secondary electrons. For example, ozone has a ionization and then recombination path that includes spinning off a secondary set of electrons. Shenanigans gets ridiculous. My goal is to hide as many of these sins as possible in the in the end of this kind of loss field idea. And to kind of go in and say sort of build a mapping from you know, from my baseline loss, my changes to the baseline loss into, you know, hey, my measurement of solar intensity, which is F10.7, which is your intensity of 10.7 centimeters, is just kind of a stand-in for UV intensity, and my BZ term, which is a function of geomagnetic storming and blah 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 blah, right? My, say, O2 density and all this stuff, right? So this will be kind of an environment vector that will input into a simple transformation off of my baseline. And so that'll be the model, right? And it's not going to be great, but it should be a good, easy to apply. I don't have to sit here and have my damn computer crunch or ray tracing program to get a first look at what I expect my losses to look like if I'm going to transmit from here to there at this frequency. All this stuff is also a function of time of day, right? Because your UV intensity is all purely solar flux. So at night you don't have that solar flux, so your ionosphere changes dramatically, and so your losses change dramatically. What's going to happen is if you're as your electron density goes down, right, the if I still have high enough electron density to actually reflect my signal, I'll see less losses in the signal. But if the signal frequency is higher than the plasma frequency, now that the plasma frequency has been reduced, that signal will go straight out to space and I'll get no reflection at all. Yes, but if I'm doing this in terms of a model of, right, so this is sort of a semi-engineering problem set in that I don't expect a single transmission path to be sitting up there for 12 hours. But if I'm sitting here and sending off a signal in one direction, and I'm curious what my loss is going to be at this point, if I'm even going to get to that point, right? What my loss is going to be at this point, what that's going to look like as my day progresses is going to change. So, so I have a whole bunch of this other data from this huge collection campaign called HiDive. Let's see, do I have any of it actually in my in here? Okay, well, you can sort of see this. Right, so there's this big data campaign that took place using one of NIST's transmitters and a bunch of receivers, 3 receivers, for like 5 years worth of collections. So there's a lot of, hey, we have solar flares in this. Hey, we have day nighttime collection, and we're looking at what our signal strength is at each of these receivers over, years, literally. And so the goal is to tie some of this stuff back to what's going on in the ionosphere, because ultimately we're trying to say, hey, what's causing, these sorts of loss? Like if I plot my losses over the course of a day, I'm going to get a certain curve at a certain frequency. What's causing the features of those curves, right? What can I say that if I have more O2 floating around at 80 kilometers, how is that going to affect the losses I would expect to see during the day at this frequency? And because those, for example, those neutrals like oxygen density, those are influenced by time of year. So if I'm going to say, well, I expect to see, so in addition to kind of daily oscillations, I'll see annual oscillations. And oh, hey, I care about solar activity, and that goes on a 13-year cycle? Is it 13 or 17? I think it's 13. So there's like all this other stuff that's going on in the background, right? And so it's like, all right, how do we take all this shenanigans into account to the point where we can make a sort of, in a sense, it's mixed in with a whole bunch of other stuff, right? So you're is that what you're doing? You're looking at O2 concentrations? Where oh, me, yeah. Kind of. Yeah, so it's not just O2 concentration. So I have some historical data and models for things like O2 concentrations, N2 concentrations. MSIS, frickin', I can't remember what that abbreviation stands for, is a model of neutrals that are going on in the upper atmosphere, right? And so the different neutrals are going to have kind of different absorption characteristics to it. And some of the neutrals, the more of them that are up there, if they're sitting at the altitude where they can absorb the right part of the UV spectrum, then those are going to actually be supplying my electron densities. So some of these densities might actually be amplifying the amount of losses or amplifying the amount of electrons up there, because these are being ionized by some of the stuff. Oh, cool. So are you doing like quantum computing stuff? Sorry. Shiny object. Oh, okay. Very neat. That's really, I sort of avoided a lot of quantum mechanics. I didn't avoid, but quantum mechanics was never my strong suit. Gotcha. A lot of those are emergent behaviors of like crystal lattices and stuff, right? Because I'm thinking of things like metamaterial type properties. Okay. Yeah. So I've done some stuff with metamaterial type structures, but at RF type scales. So where your repeated structures are sitting at like half a centimeter. And you can do some cool stuff with them. Electromagnetic and external magnetic field. Yeah. That's really cool stuff. Yeah, a lot of that stuff is like whew, over my head when it comes to I haven't done a whole lot of solid state physics as much. Most of my stuff has been in either I've done a fair amount of the electrodynamics, and I've done a bunch of obviously the plasma stuff, but I haven't really done solid state. Okay. Yeah, some of the organic molecule stuff is really cool. I have bounced into things from time to time. I haven't really dived too deep into that. Yeah, I just sort of wandered my way into this space weather area of the world. Yeah, that is so weird. Because it's really, I mean, if you think about it, right? The Maxwell's equation, there should be some parallel to it, and just is just wave mechanics. Really, it's wave mechanics in different under different potentials. But yeah, I mean, you have so many. The setups are so different. I can imagine that because you're looking at spin alignments and all that kind of shenanigans using magnetic fields, and that's really cool stuff. But yeah, it's flipping. That is a little bit beyond what I've done in those sorts of areas. Like I said, I've done some Green's function stuff in relation to like FEM, because I took a computational electrodynamics class, and so a lot of that that ended up in the Green's function world of things when we did a little bit of not FEM. What's the other one? It's FDTD. We did a whole bunch of FDTD stuff, and FEM, and I cannot remember the third one off the top of my head. I'm trying to look at the books I have sitting over there. I know I've got it somewhere. That's finite element. Maybe it was finite element. Is finite element the Green's function one? Or is it the other one? I might be. It's been a little while. I might be confusing myself. Anyway, wow. I just. So finite difference is solving propagation equations. So it's used in electrodynamics. It's also used in fluid dynamics and a few other things. It's just solving the partial differential equation in like steps, right? So you kind of grid up the region, and you say, okay, I can solve for these points. I kind of so it's finite. Yeah, it's finite difference time domain. There's also a finite difference frequency domain version of this where you just flip over to the Fourier domain and do the same sorts of thing. But you're kind of doing the magnetic. You have essentially two grids, one for the electric, one for the magnetic fields, and they're kind of half a time step away from each other. And you're just looking at how they influence each other, propagating along this grid. And you're solving Maxwell's equations at each of these points using the different elements. you're just kind of bootstrapping your way around. Oh my god, this is gonna bother me. Hold on one sec. Difference. Element. I'm gonna remember it later, and it's gonna bug the hell out of me. And I know I have a stupid. Yeah. Oh, so the big problem, like theoretically, so theoretically it'd be great to do finite difference in the ionosphere. The problem is, your lattice has to be like, you still have the lambda, the sampling restrictions from von Neumann. So you still have to sit there at like at least two samples per wavelength. And yeah, your wavelength is pretty long, like 10, 50, like 50 meters, say. And then, okay, well, now I need to do that over thousands of kilometers. And so it just gets to be these unbelievable, ridiculous things. You can do, if you're going to propagate it, you can do a phase screen approach where you sort of make a bunch of approximations, and then use freaking Fourier optics to propagate the phase front between points. And you're kind of assuming that things are the same between those points, or are relatively constant between those points. Hi, Toasty. How are you doing? Hope things are doing well. See, that's a valid assumption, actually. Because things always change between points. But anyway. So yeah, so woohoo. Busily trying to math. Our Roman 2001 over here is someone who has a lot of physics background, is doing some really cool physics stuff. That's over my head. But no, continuity of the medium in space, right? And yeah, you're also doing continuity of space assumption as well, but you're sort of converting it into like a two-dimensional slice, and then you're saying, okay, if I propagate it through something that looks like this, it should look like this at my next point, right? And so you just kind of do this phase, it's called phase screening. But so you can kind of do that over those huge distances that you're looking at here compared to your wavelength. But that's really the only way you can do proper propagation stuff. And what's really interesting is this is in fact valid. I do not disagree at all. Oscillators are cool. My brain was gonna say, oh, right. So I've done some of this phase screening things where you're like, typically they assume you have this like Gaussian smooth cloud of plasma that you're propagating your signal through. And then I looked at some data from the Arecibo radio telescope, where they had sat there and they just did like a vertical look, and then they let all the ionospheric plasma sort of just drift overhead over a period of time, and it looks exactly like rain clouds do, but at a larger scale. So what's happening is you don't have this nice smooth clouds that these things are interacting with. No, you have a very complex shape that's affecting things like the phase of the signal as it goes through them. So it but it's like trying to describe clouds and weather and all this stuff without being able to see it. Right? This is the problem. It's really hard to actually detect things on that sort of level to where you can see the the complexity or the physical shape of these clouds of different gases and electrons and all the things they're doing. I have an evil project in mind eventually to try and do something like that imaging, just using a local AM radio station, and essentially trying to set up an inverse SAR radar type thing, but just pass it. Like I'll just have some AM radio receivers and look at the reflections over long periods of time and try and see if I could do any defining the shape off of it like a SAR. Yeah, you can do some of that stuff, right? And you can make. So what I ended up doing actually is I ended up literally taking the image. I rather than assuming a sort of Gaussian blob of plasma, I literally took the image and converted the image within my my grid that I was simulating. And I just plopped down that image as the intensity, the image intensity as electron density and or plasma intensity, essentially, right? So I just mapped that image onto the area that I was running my simulation on, and I got some interesting effects that were seen that you didn't see in some of the older simulations. So that was cool. You get scintillation in signals that propagate through it. Let's see, what was I doing? I mean, yeah, you have to. What was I using to do that? I think yes. I mean, I've done this all in Python because I am a bad coder and I don't know how to use C. But I believe I did use GPU acceleration for that stuff. I want to say I used. I don't remember which package I used. That was a while ago. That was for my master's. But yeah. That was a fun project. But for this project here, right? So what essentially happened for this project is I got handed this giant freaking data set and was told, go find something interesting off of it. And come back with some interesting results. So yeah, I've got some stuff. But if I can come back, I'm trying to bring back what's essentially this giant set of amplitude measurements. I'm trying to bring it back to specifics of the ionosphere that I can point to, and then use that, right? Leverage that into a predictive model. So one of the things that I'm doing is seeing if I can use all this data that I have essentially as a training set for a relatively simple model. And it works better than just like a simple median type setup or something like that. But there still is my next thought is to do something like a the equivalent of a what's it called? Match filtering kind of system, but like one of those predictive sorts of things. But again, that starts getting into this really high computation world, and the whole goal of this is to make something that's someone can pick up and relatively easily use with few inputs, and get something that's good enough to where I can say, okay, well, even if you were to run like a full modern ray trace that might take you a few hours, you'll only, it'll be better, but it'll only be this much better. So for for a first hack functional guess, that's probably pretty good. Right. So that's the goal. But the way I'm trying to tie it to the physics of what's going on is through this loss field concept, which means, again, tracking down how I can theoretically predict the space weather. So one of the difficulties of the D region. So the D region has been which is the bottom of the ionosphere, has not been studied very intensively, and there's a few reasons for that. One is, you've already absorbed most of your UV that's going to be absorbed. So your electron density is relatively low down at the D region. So it tends to affect lower frequency things. So this is where things like AM radio might get affected strongly. The other problem is you're low enough that thermal mixing and terrestrial weather have a stronger impact. So you end up with these additional sorts of complexities down there. And so people just sort of looked at it and said, we don't need to worry about that. Let's look higher up in the ionosphere where things, the thermal mixing sort of stops and things start stratifying by densities. And so you can say, so it's a lot easier to deal with. But that's one reason why you get these specific electron profiles is your relative densities of the different components changes as you go up in altitude. And so each of those components is absorbing different portions of that UV spectrum. And so they're ionizing to different degrees. And so you end up with something that looks kind of like if you were to map the sort of your plasma intensity as measured by electron density, with altitude, right? So this is E minus, and this is altitude. You end up with something like that. Yeah, so there's a few different goals for this, right? One of it is teasing apart some of the specific impacts that these different environmental conditions, be they space-oriented, geomagnetic, or neutral density, right? The impacts of those things on the lower ionosphere, right? So what's that actually doing to the chemistry and the contents and the electron density sitting at the lower ionosphere, right? That's part of it. The other part of it is more functional, because I'm also tied in with people who are interested in this for communications and that sort of thing. And for them, they sort of care about this in a operational radio propagation sort of manner, right? And so for that kind of community, it's more of a, hey, can I provide a functional tool that will help you? And some of that is, for example, the people who do ionosons, which are kind of the typical, I radiate straight up and I'm looking at the reflections at different altitudes and I'm looking at what my electron density is, right? People who care about things like communications, satellite communications, GPS, for example, right? So you can end up, the ionosphere can end up causing scintillations and what's it called? Phase delays in GPS signals that are propagating through it. And so if you're working at like a, really high fidelity level of GPS, for example, NIST cares about this, you can start having effects on GNSS accuracy, right? So those sorts of things, it matters for a lot of those sorts of areas. So that's kind of the functional piece of it. So that's the more engineering interest in it. And then the more physics interest is, hey, what the hell is actually going on down there or up there, down there at the bottom of the ionosphere, up there from us. There we go. Make Tesla's GPS better, or make someone's GPS better. Yeah, I mean, it's in an intense flare, solar flare kind of conditions, these can really matter. Because you end up with especially the lower ionosphere gets really amped up in strong solar flares. And signals, you'll end up with loss of signals even at higher frequencies that are more typically used in modern communications. You can still get signal degradation and absorption effects and all these kinds of things at these higher frequencies when you have strong solar wind influences. There are other things that impact the ionosphere. For example, you wouldn't think it, but meteorites, right? There are all kinds of meteorites that are, or meteors that are constantly, small ones that are constantly going through the atmosphere. Well, as they ablate going through the atmosphere, guess what they leave behind? A whole lot of metal. And that metal can interact with radio frequency stuff, and you can have similar effects to essentially boosting the electron density in this region. So you can end up with meteorite or meteor impacts on the ionosphere. And actually, this is how meteor radars are able to track them. Is they're actually looking at a lot of the reflection that's coming from the ablation from the metallic meteors as they come through. So there's a lot of really cool applications in that realm. Yeah, so that's sort of where these things go. Ooh. Oh, that's cool. Non-violent. Because usually when I think, I guess no, because I guess you are, it would keep it. Usually when I think of spin direction, I think of things that are pretty strongly impacted by stuff like thermal noise and things like that. But I guess no, I guess in a crystal lattice it would maintain better, like it does in a permanent magnet. Yeah. Oh, oh, that's so cool. So are we going back to spinning drives? To the spinning drives. Finally get away from these, from the solid state, the solid state mafia. Only spins will spin. Nice. Yeah, there's some really cool man, yeah, what's it called? Solid state physics is freaking awesome. Trying to think, I haven't done anything like that. The only thing I've ever done is I took a course on space effects on microelectronics, essentially, right? Where all of a sudden you have a freaking cosmic ray coming through and screwing up all of your data. And what's kind of the degradation rate of memory and things like that. And it'll deplete PN junctions and all this kind of shenanigans. It'll punch extra holes in your PN junctions. That was a fun course, actually. I like that course. But yeah, solid state is a brave world that I have been far too scared to actually enter. Okay, all right. I mean, in the end, isn't all of it? It's also some version of, here is a set of PDEs that describe this. We can't actually solve any of these things, but we gave it, but we've been chunking through this in the computer. I feel like that's what physics ends up falling back on eventually. But variation, yeah. So I have a question for you, since you are familiar with it. Have you ever done Feynman path integrals? Because I spent some time trying to teach myself some of it. And I'm a long way from actually functionally teaching myself how to make it work, but it's something I'm interested in, and it's something that again comes up here potentially in terms of ray traces. But I don't know what the Lagrangian that you'd be integrating would be. I'd have to think about that. I'm not sure. I'm not sure what the path itself that you'd integrate the Lagrangian over would be for something like an RF, signal path, like propagation path. Everything's a variational calculus problem. Yeah, that's true. Okay. Yeah. Yes, you're sparking a few neurons. I do remember partition function stuff a little bit. Not enough to actually apply it, but I do remember a little bit. I remember of its existence. Yeah, some of those Lagrangians just get obscene. Like, absolutely insane. Huh. Wonder... Yeah, because, I mean, you're trying... Yeah. What does Lagrangian like that look like? I don't know what you're pretending... Yeah. P4 model. Okay. I don't know that off the top of my head. Okay, like exposed on... Okay. Oh, boy. So a lot of quantum field theory, QFT shenanigans. Yeah. Somewhere. I don't know where the book is. Oh, okay. Okay. Well, that's cool. How do you apply that to? I'm not gonna ask. I'm getting distracted. Like, how do you apply that to the? Does the quantum interactions not have issues with trying to do that classical approach, or is it just that you're doing it? I guess. Huh. Sorry. Uh, because there's no direct equivalent to spin in classical mechanics, but I guess you just use normal what's it called, the angular momentum as a stand-in. Huh. No, it's really cool stuff. It's really cool. Oh, I see. Okay, so you're just kind of bundling everything up in there. That's kind of what I'm hoping to do with this, is just kind of take a lot of these details that I'm trying to look at and bundle them up in a in a nice little yeah, it's all sort of in here somewhere. But we don't have to deal with this because we can hope this cancels out somewhere. Yeah, it's a lot of fun when you can, like I said, hide a lot of sins behind constants like that. Uh uh yeah. So hold on. Uh reminded me of something. It sure reminded me of something. One second. I want to close this again. If Oh, that's an idea. So if so I was trying to figure out how to compress this into 2 dimensions. Sorry, my brain just what if I just did everything in terms of the direct magnetic field line directions? Kind of like what you were suggesting a long time ago, and I was like, I don't know. Ooh. Because then I could theoretically maybe compress this into 2 dimensions. I'd have to look at the multipathing element, but that would be a way to do it, right? Because then it's just, you would just have what I wanted, which is R and theta. It's just the zero of the theta would be yeah. So just a heads up before you go, just to tell you what I sort of doing. Usually on Sundays, I will take some random paper and just try to walk through the paper. Usually it's something I don't understand, so I'm trying to like describe it, explain it, and understand it as I go through the paper. So I do that Sunday mornings. Wednesday, I usually take a break from math and do some reading or some gaming. And Friday is sort of I'm trying to figure out stuff for my research thing. So I'll do a little bit more of the mathy maths. So yeah, feel free. Thank you so much for coming in. Get some good sleep. It was great talking to you. And absolutely anytime, feel free. Yeah, thank you. It was really great talking to you. Oh man. Okay, so if I think of it that way. Let me see. How does that convert? How's that convert? Right. So this is, I need to go back to this paper. Where's this paper? Great. Empty citation. Where the stupid paper? What paper was that? That was the where did I put that paper? Oh, I put it down somewhere. Where did I put it down? Did I put it down here? Where was it? Where was it? What are you? What the devil are you? Hello? Hello? What are you? No, you're just not gonna open? Okay, cool. Uh-huh. Where is that stupid best friend? No, it's not there. So it's gotta be under. Bow. No, 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 and no. Where on earth did I put this stupid? No, 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 no. No, no, no. Here we are. Where are you opening? What are you, computer? What are you doing?
Computer? See that man.
Okay. Can I open it with DuckDuckGo? There we go. There we go. Okay, so here's our RCS paper. Okay, so we've got so what I'm gonna do is I'm gonna write out the math that's in this paper into my not you. You. Okay. So we're gonna go like this. All right. So I'm gonna say begin what? It's not begin subsection. It's just subsection. Subsection Anosphere RCS math. Okay. So we're gonna. Okay, so the resolution volume cell, sure, we don't care about that. Okay, so we're gonna say so delta, oops, begin equation now. Delta V R comma theta comma, v equals frac pi 4 r squared. Oops. Yep. Delta r theta 3 phi 3 no, was it not a prox. Was damn you, LaTeX. Approximately equal. Yes, that one. It is a prox. What? Did I do it wrong? APPROX. No, I did it right. I just didn't look. R squared delta R. Oh, it just removed them. Sure. Okay. Where delta R is range resolution, 3 dB beam width and azimuth and elevation. Okay, so delta R is range resolution. Theta 3 and phi 3 are 3 dB beam width. As L. All right. So so RCS of volume is is begin EQ begin equation. All right. So sigma equals R squared delta R beta 3 B 3 eta. Right. Delta R. Sure. And now eta is reflectivity of the effective scatter volume, which is formed by the intersection of the radar beam and the atmosphere. Okay, so where eta is reflectivity of effective scatter volume of intersection of radar beam with ionosphere. Okay. Okay. Considering the attenuation of electromagnetic waves propagating the ionosphere and using approximation 6, we can reduce equation 3 to that. Right. So then equation 3 is which? This guy. So it's that integral over the volume ends up becoming LSLP or LSNLP. What's the difference between those? So LS is, I assume LP is propagation loss and LS is system loss? Question mark? Yeah, system loss. Okay. Okay, so they just tagged that on. Okay. So then backscatter, scale irregularities. We observed by HF swarm from the plasma of the IS irregularities, skill size are highly anisotropic and aligned with a geomagnetic field B. The reflectivity of ESV depends on the direction of the electron density and scale size of irregularities and can be expressed as it is raw. Right. K is the radar wave vector. Is your velocity. Okay. But thank you for coming in, and yeah, it was great having Roman around. Hopefully they'll come back for another time. Yeah, it was good being able to talk to someone else kind of in the area of study ish. Let's see. Namely K. Okay. So, right. So then for us, it's going to be a little different, right? Oh, geez. Bye. Oh, I think I have to go to a thing. Hold on one second. I might need to go. I might have. Hey, B, do we need to go? Do we need to go? You don't want to go? You sure? We don't have to. I realize what time it is. Because he was being good with me before, so that's fine. I've been going for like 2 hours, so it's perfectly fine. Okay, we might have a doggy visitor coming in, so we'll see how that goes. All right, where were we? Right, so sorry. Well, I'm just like right now copying these pieces over from this other paper, and what we're going to do is we're then going to adapt them as we need to for our stuff, right? Hey, Mr. Potato Pants. Hello, Potato. Have you come to solve all of our problems? Oh, yes. I've been told the answer is 2 tail wags and an ear scratch. And I should have known that to begin with. Huh? Excuse you, what do you want? What do you need, Mr. Potato? Yeah? What do you want? Yes, I see that you want something. What would you like? What do you want, Mr. Potato Pants? You have Monkey here? You want Monkey? Monkey. 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 We're not chewing Monkey. Okay, you don't have to chew Monkey. If I go back to doing this, are you gonna cause chaos again? The glint in his eye says yes. You gonna cause chaos? You gonna cause chaos? Good boy. Good boy. I love you. I love you, Potato. Ah, such a little chaos causer. Yeah. All right, let's see what he does. Right. So what I was saying, I'm kind of transferring the math piece over from this other paper that I am going to be citing in here, because they have something that's like adjacent to what I'm doing. So I'm gonna take what they've got in here right now, and then we'll hack it up in a way that makes sense for what we're trying to do. Excuse me. Right. So, show. All right. Where are we? Okay. This is for what did I say it was? This is for an elliptical beam. This is, how do you spell that? ELLIPTICAL. Beam. All right. Also, I wanna. Does this have a? I need to add this. Let's see. Copy. Let's go ahead and search for this. Yes. Now give me the no, I don't want that. I want the not references of this. For radar reflections. No, I want the citation for this. Cite this conference paper. Here we go. Here we go. I don't know where Potato went. Oh, he's just laying down. Good. See. MB was worried that if she let him upstairs, he would cause problems. Pfft, that dog never causes problems. Hello? Oh, thank you. There we go. So we should be able to go over to our bibliography and go. Probably don't need that. Well, doesn't really matter. Shoot, I want to convert this to from BibTeX to let's see. IEEE. No, wait. Where's mine up here? Ah, mine are up there. That's why. LaTeX is interesting. That's weird. Let's see. Ionosphere. Yes. So now, if we go here and we go site ionosphere. Yes. Now when I do this, it should show the citation as a thing. Right? 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 Yay! It's live! Wow. Okay. Where was I? Cool. So okay, so atmosphere. Go away. Okay, and then good that we have that, and we can close this, and then he's being pretty good. So we could go back up to our first PR. Let's just copy and paste this guy. Okay. Okay. I'm just gonna remove this label for now. Begin equation. So now it's. Did I really pick the wrong one? Potato, it's okay. It's really okay. Sigma. This guy. This is what I wanted. This is what we wanted. There we go. Okay, so now it's this, but then we also need delta R theta 3 B 3 eta over 4 pi cubed R squared. Oh, interesting. Right. Because we had the R squared from there. Oh, that's going to be interesting because the sigma had the R squared on top, and when we put the sigma on top of the R squared. You monkey? You monkey. Monkey. Yeah. Monkey. We've got a little monkey toy, and we're playing tug with monkey toy. Tug with monkey toy. Yeah. I've got monkey. I got. Oh, God. It's dog pull. You are not a tiny dog anymore, are you, Potato? He used to be so small. He was let's see. Him and his crate and all of his stuff was 19 pounds when we brought him home. Because we had to fly him. He is now well above 19 pounds. Aren't you, Potato? He's probably like 3.5 feet long. He's a very long dog. He uses his long to the detriment of all of the stuff in our environment. He likes to reach up to high shelves and to kitchen counters. Those are always fun, right? Different ways that we can exploit our long. Oh, good boy. Long with the floppy ears. What I'm gonna do is, oh, hi. Because it's gonna be a little different for what I'm trying to do. Yeah. I'm gonna keep the R squared up top and the R to the fourth on the bottom. R squared. Okay. Because that's gonna matter to us later. Later. Right. Oh, there's no sigma. Got rid of the sigma. We've gotten rid of the sigma. Okay, fine. And then he goes into Bragg scatter conditions, right? And then he says eta. Okay. Here's wave vector in the medium. VD is the drift velocity of the irregularities. Theta or phi is the flow angle, the angle between the radar wave vector and the drift velocity. Alpha is the aspect angle, i.e., the complement of the angle between K and B. And L is the scale length of irregularities. Fe is the electron and neutral collision frequency. Delta N is the average level of electron density fluctuations. Ne is the electron density of irregularities. Yes, you. Why are you using your long so much? What's up there? What's up there, Mr. Potato? That you would grab things with your long in such a brazen manner? Hmm? Oh, good boy. Yeah, you got a squeaky toy, huh? Did we put Monkey aside for... What was that, lamb chops? I forget. You're a good boy. You're a good potato. Oh, back to Monkey. We want more Monkey Tug? Monkey Tug. So, B, when she went to Costa Rica recently, brought him back a stuffed monkey toy, capuchin monkey, that we expected to last about 25 seconds and has lasted quite a bit now. So it's actually impressively well built capuchin monkey, stuffed capuchin monkey. He did tear out the eyes because the eyes were like, hard beads, and so they were an easy target. But anyway. Okay. So let's see. For conveniences, equation 10 can be reduced to. So hold on. Right? Eta is supposed to be the RCS per cubic meter. Right. But this is just some function. RCS per cubic meter. So for convenience of discussion, equation 10 can be reduced to 9 and 10. What are these? Atmospheric regularity for your back scatter measurements. Refractive indices of scatter volume. Oh, what's this one? Ooh, hello. Why, hello. Give me that paper. Give it to me. Okay. Cool. Give me the PDF. Oh, give me the PDF. Give me the PDF. Give me the PDF. Okay. Oh, this is going to be important. Okay. Large amounts of integral from the phase refractive index along the ray, right? And yes, sure, yeah. Okay, this is where he's getting the back scanner. Ooh. Oh, it's this paper. I've seen this one already. Okay, so when they say that they got this from Walker et al. Okay, 7. Okay, determine the fluctuations of. Okay. So can we find this paper then? What are you chewing? He's chewing on something. I don't know what it is, and that's kind of concerning. Okay, I'm gonna have to get this on my other thing over here. I'm sorry, you're just like sitting there bored as hell. As I go through this PDF, please. Oh my god, access orientation. Let me just make sure that this is not being shown. Okay, beautiful. Let's not self-docs. There we go. Okay. We definitely want to download this. Let's see. I think I've downloaded this paper already. No, I haven't. I don't think maybe I haven't. This will be a good paper for Sunday. This is too long for a Sunday paper. This is a good paper for me, but it's a little bit too long for a Sunday morning paper. Okay. But this is useful. This is useful. It's useful. We're gonna keep it up. What was I doing? What is my life? For a change, it will all be made clear. For tonight is the meaning of life. Oh man, I have to hold on. Sorry. I got distracted. Not gonna do it on here. Yes, potato. Monty Python, meaning of life. Mrs. Brown lyrics. See if I can find the Galaxy song. Can I sing you a song? Would you be terribly upset at that? If I were to sing you a song? I cannot sing. I have no ability to sing. But there is this song in Monty Python that I used to have memorized. So Monty Python's meaning of life. Whenever life gets you down, Mrs. Brown, and things seem hard or tough, if people are stupid, obnoxious, or daft, and you feel that you've had quite enough, just remember that you're standing on a planet that's revolving at 900 miles an hour. Okay, I'm not going to sing because I can't sing. Also, my voice is dead. But It's funny. It's funny. Oh, jeez. I think this is winding off into chaos. Yeah. Yeah. Potato, are you causing... One second. Let me see if potatoes causing problems. No, you're not causing problems. I eat potato. Would you be terribly upset if we transitioned to playing a game? I think I might transition to playing a game. Potato, what are you doing? Maybe I won't transition to playing a game. Potato, what's up? You gonna lay down? Oh. I'm hoping. That's a book. You cannot chew the book. Yeah. Yeah, you. Please do not chew the book. Hi, I see you. Yes, you're very cute. I agree. You are ridiculously adorably cute. And I love you. Can you please lay down instead of chewing the book? That would be most excellent. Maybe? Hello. Hey, Puppins. Hi. Now lay down under the... No, of course you don't. Don't you go near those cables. Okay. All right. Well, I guess we're not going to be playing games. I believe the unlimited patience of Potato has in fact run out. So thank you very much to everyone who decided to hang out here for some unknown reason and listen to me spout nonsense. I very much appreciate it. Very, very much. Potato, get down. No. Yes. Thank you again so much. Our next planned stream is, of course, the Sunday morning paper, which is planned for Sunday at 10:30, I believe. If I remember correctly. Potato, don't do it. That's super helpful. Yeah, I believe it's 10:30. We will be continuing a paper that we started. It is in line with what we've been doing today, but we will continue that along. Potato. In the meantime, let me see if I can't find anyone else doing anything physics-y to raid into. No idea what that is. Boop, 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 boop. Blah, 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 blah. You know, I've noticed that science and technology tends to have a lot of people that are just like streaming some data set from somewhere, like weather or let's see, surf cam. Really? Someone's got earthquake, solar, and weather radar just streamed. So few people are actually doing There's a few engineering. There's some engineering stuff that's going on, but anyway, let me see. Is there anyone else online that we could raid into that would be of interest? Not really. I don't really know any of these people very well. Okay. I'm sorry. I will leave you without a raid. Thank you so much for, again, coming here, hanging out. Thank you, Toasty. Thank you, Mark. I know you're floating around there in the background. Just thank you for putting up with this. It is very appreciated. Potato, I swear, would you stop? Oh, okay. Oh, I'm sorry. I thought you had a wire that you were chewing on. Anyway, thank you again. I will see anyone who cares to swing by for a paper on Sunday. So it'll be a little more structured and a little less rambly. And then, of course, Wednesday we will do our next section of Lords and Ladies by Terry Pratchett. Yeah. So, Potato, I wish you all the best of weekends. Hopefully some downtime, relaxation. I will see you all in a few days. Goodbye.